Welcome dear students once again to my YouTube channel Knowledge Entertainment. Before moving on to the topic where we have ended in the last video, that was relations. So we move ahead in the relations in the second part of this video, namely relations and functions. So one more important relation is empty relation. Empty relation. As we have seen in the previous video, that if A is having number of elements as P and B has number of elements as Q, then number of elements of A cross B is P into Q, and since every subset of A cross B is a relation, so total number of relations from the set A to the set B is 2 raised to the power PQ. This is the total number of relations from the set A to the set B, where set A is having B elements and set B is having Q elements. Since every subset of A cross B is a relation, and we know that empty subset is always a subset of every set, empty set. So here the empty set is also a relation from the set A to the set B, and this relation is known as empty relation. On the other hand, we also know that every set is a subset of itself. So A cross B is a subset of itself, and since every subset of A cross B is a relation, A cross B is also a relation, and the set A cross B is called universal relation from the set A to the set B. Another very important question is, okay, what will happen if set A and B are same? So if we are talking about the relations from A to A, then we will have to consider the Cartesian product A cross A. And if A has P elements, then A cross A number of elements will be P multiplied by P, that means P square. And since every subset of A cross A is a relation on A, therefore number of relations on A will be equal to number of subsets of A cross A, and we know that if a set has n elements, then number of its subsets is 2 raised to the power n. Here A cross A is having P square elements, so number of relations on A, that means the number of subsets of A cross A will be 2 raised to the power P square, and that is the number of relations from the set A to the same set A. Now we move further ahead. There are some examples. In the previous video we have talked about reflexive relation, symmetric relation, transitive relation, and equivalence relation, which is reflexive, symmetric, as well as an equivalence relation. So let us consider this relation. Let A be the set n, the set of all natural numbers. Let R be a relation on the set n consisting of all ordered pairs of the type AB such that 3 divides A minus B. This is the relation. The ordered pair AB will be there in the relation. If A minus B is divisible by 3, that means 3 divides A minus B completely. Now let us look at this relation whether it is reflexive, it is symmetric, it is transitive, or all of these. That means whether it is an equivalence relation or not. So first we will check reflexivity of this relation. Reflexivity. And this relation will be reflexive if ordered pair AA belongs to this relation for every A belonging to the set of natural numbers. So let AA be an arbitrary member of n cross n. If this AA belongs to this relation, which is an arbitrary member of n cross n, that means for every A belonging to n, A will be related to A, and that means the relation will be reflexive. So let us check whether it belongs to or not. It will belong to AA. This ordered pair will be a member of R, if this condition is satisfied. That means if 3 divides A minus A, that means if 0 is divisible by 3, and we know that 0 is divisible by every natural number, so why not by 3? So 0 is divisible by 3 is true, which is true. And 3 divides A minus A means AA belongs to R is true. So therefore AA belongs to R is true for every A belonging to the set of natural numbers. That means every member of the set n is related to itself, which makes the relation reflexive. That means this relation is reflexive. Next, we move on to the second property, that means symmetricity. Let us check whether this relation is symmetric or not. So we are going to check symmetricity of this relation. Let AB be a member of this relation. Now, symmetricity says if AB belongs to R, then BA, the reverse ordered pair, must also be a member of R. So what will happen? AB is belonging to R, and if AB belongs to R, this relation, then 3 must divide A minus B. Then that means 3 divides A minus B. And we know that if 3 divides a number, then 3 also divides its negative. So here 3 divides A minus B means 3 divides completely its negative, minus of A minus B. This means 3 divides B minus A. When 3 divides A minus B, AB belongs to R. So if 3 divides B minus A, what will happen? BA will be a member of R. So we have taken AB belonging to R, and we are getting BA belongs to R also. That means whenever AB belongs to R, BA is also a member of R, which will make this relation symmetric. So this relation is symmetric as well. Now we move on to the third property, whether this relation is transitive or not. That means we are going to check the transitivity of this relation. So for that, let AB, and keeping the second member same, BC. Let AB and BC be two members of R. A is related to B and B is related to C. If A is also related to C, that means if AC belongs to R, the relation will become transitive. So let us check whether it is true or not. AB belongs to R means 3 divides A minus B. A minus B. BC ordered pair also belongs to R. That means 3 divides B minus C also. And when a prime number divides two numbers, then it must divide their sum. So if 3 divides A minus B and if 3 also divides B minus C, then 3 must divide their sum also. Their sum means A minus B plus B minus C. Here B will be cancelled out, and what we will get? 3 divides A minus C. When A minus B is divisible by 3, AB belongs to R. So when A minus C is divisible by 3, what the result we are going to get? That AC belongs to R. That means A is also related to C. A related to B and B related to C we have taken, and what we have obtained, that A is also related to C, which makes the relation transitive. So this relation on the set of natural numbers is reflexive, symmetric, as well as transitive. So that means this is an equivalence relation. So wherever there is an equivalence relation, there will be equivalence classes, which we will discuss in a later chapter. Now we move further ahead from relations onto functions. What a function is. It is very important as well as very interesting topic to understand what a function is, and functions are basically the roots of all the mathematics, especially algebra. So you must understand the definition of function first. So what a function is. A function is actually a path, a way, which carries each and every element of a given set to a unique element of another set. So I'm going to write here a function is a way, or you can say a path, which carries each and every element of a given set to a unique element of another set. Another set. So you can also say that a function is a relation which associates to each and every element of the set A unique element of the set B. It is another alternative definition of function. So what is generally happening? Suppose here you are having a set A containing some members, say 1, 2, 3, 4, 5, 6, 7, and here is another set B, and members of B are A, B, C, D, E, F, G, H, I. So what a function is? A function from A to the set B. What it will do? It will associate each and every element of this set, the set A, to a unique element there in the set B. Suppose it associates 1 to E. So if 1 is associated to E, now 1 cannot be associated to another element, because every element is associated to a unique element. I am giving stress on unique element. Similarly, 2 is also associated to some element, say B. 3 is associated to a unique element, say F. 4, it may also associate to the same member B. We are not saying that every element is associated to a different element. 2 or 3 or more elements may be associated to the same element, but each element of the set A must be associated uniquely. So this is the basic thing to be clear. Suppose 5 is associated to H, 6 is associated to C, and 7 is associated to E. Suppose this is our function. Now we call it as image of 1 is E, and we write it as f of 1 is equal to E. Similarly, we say image of 2 is B, and we write it as f of 2 is equal to B. Similarly, we call image of 3 is F, and we write it as f of 3 is F. We say image of 4 is B, and we write it as f of 4 is B. We call it image of 5 is H, and we write f of 5 is H. Similarly, image of 6 is C, and we write f of C is C. F of 6 is C. And similarly, image of 7 is E, that means f of 7 is E. One question may arise in your minds: why we are calling members of B as images of members of A? Image, from where the word image has arrived. Actually, the function is just like a mirror. It is just like a mirror, and whatever is there in front of the mirror, behind the mirror, you are getting some images. In a real mirror, every person has a unique image. I can't have two different images. You can't have two different images. No one in this world can have two different images. We are all having only one image in front of the real mirror. The next question, then, why the same image is for two different elements? Yes, it may happen. You may have seen many Bollywood movies where there are twins having same image. So they are actually the twins having the same image. If they are twins, image of 2 and image of 4 will be same. So it is working like a real mirror. Now, the set A is called domain of the function. The set A is called domain of the function f and is denoted by D and subscript f. Similarly, the set B on the other side is called codomain. It is called codomain of the function f. And normally we don't have any symbol for codomain. We can just write B is codomain of f. Now, there is one more thing. In the codomain set, there may be some elements which are having no pre-image. Like A is here. A is not image of any element of the set A. That means A is not having any pre-image. Similarly, G is there. G is not image of any of the elements of the set A. That means G has no pre-image. Similarly, there is I. I is not the image of any element of the set A. That means the element I has no pre-image. So only the busy elements in the set B are what the elements are which are busy. Busy elements are B, C, D, E, F and H. So these are B, C, D, E, F and H. Only these are the members of the set B that are image of some of the elements of the set A. And this set is called a range of the set F. This is called a range of the set F and is usually denoted by R of F. R and subscript F. So this is the range of the set F. Now, there are many different types of functions. We will discuss some of them today, and then we will discuss rest of the types of the function in the coming video, maybe today, maybe tomorrow. So, first of the type is a constant function. A constant function. What a constant function is? A function is constant if f of x is a constant c for every x belonging to the domain set A. That means here is your domain set A, here is your codomain set B, here may be the numbers A, B, C, D, E, F, G, H, I, and so on. And here are some 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. Maybe the set of natural numbers. But if it is a constant function, what will happen? Image of each member of the set A will be same. So say image of A is 6, then image of B is also 6, image of C is also 6, image of D is also 6, image of every member of the set A is 6, and we write it as f of x is equal to 6 for every x belonging to the set A, which is the set known as domain of the function. So for every member of this domain, we are having the same image, and such a function is called a constant function. There are many other types of functions, signum functions. There is a modulus function known as absolute value function. There are one functions, many one functions, onto function, into function, and many others. So I am discontinuing the video here. I am stopping the video here. In the next video, we will discuss various types of functions. Again, I want to thank you for liking my videos, by sharing with your friends, and especially with the students of +1 class. So once again, thanks for subscribing my channel. With your help only, the subscription list has reached nearly 1.2k, and it will be continued with your help only. So once again, thanks a lot.